last class we were discussing about jury's criteria for stability. We saw with one example 4z4 plus 3z cubed plus twice z square plus z plus 1. We arranged the rows and we found that the system is stable. Let us take another example. This was meeting all the criteria. Let us have the denominator polynomial as z to the power 4 plus 6 z cubed plus 3 z squared plus 4 z plus 5. Is the system stable? First you apply the condition D0, it is 1 plus 6 plus 3 plus 4 plus 5, so it is positive. Okay. What about D at minus 1 to the power 4, that is minus 1, minus 6 minus 4 and 5 plus 3 plus 1, so that gives you minus 1. So, this condition is violated. You need not go for further trial, all right. You do not have to make the rows. If in the first two tests you find the conditions are not met, then it is unstable. Okay. We will take up a few problems in the tutorial class and see how to apply jury's criteria for stability. Today we shall be considering the effect of quantization. Before we go for quantization, I will just give you the basic idea about D2A conversion. You have XAT, that is an analog signal, then you have sample and hold, then actually the A to D conversion takes place. So, you get the converted value xn. Okay. Now, the analog signal may be like this. Okay. If you just sample it, it is not an instantaneous process. We sample it, but then this sampled value will be represented by binary digits by any particular code, and then till that particular value is approximately close to that sampled value, it will not stop. So, it will require continuously a fixed input. If the input keeps on changing, then it will be disturbed. So, this level has to be maintained for a period t. So, this is the sampling period, and within this time the computation has to be completed. The conversion from that exact value here to the approximate value, that binary digit, has to be completed within this time. So, that is how the sampler time is fixed, and then the next value comes, so it will stay there, then this value will stay here, then this value will stay here, this value will stay here, and so on. So, there will be some errors, of course. We are quantizing the quantity, say 5.69234.7. Now, if I in the decimal system, if I quantize it, there are two types of reducing this. One is, suppose I have 3 decimal place approximation, then I will just truncate it. So, it will be 5.692. So, the error is always 0.000347. If I have say 647, then also if I truncate it, then this will be the error. So, truncated value is always less than the actual value, all right. it can be at the most equal. So, the error is always positive. Error is one sided, actually error is actual value to be subtracted from the final result. So, it is 5.692 minus 5.692647. So, error is minus 0.000647. So, it is always in one side, but if we round it off, then it will be 5.693. So, it can be higher. So, round off error can be both positive and negative, whereas truncation error will be one sided, it will be always less, the error will be always negative. Okay. So, this whole circuit is having a value 1 for this period and 0 otherwise. So, the whole circuit output is basically like this. One may write x D2A converted value as xn h naught t minus nt. Okay. So, h naught t is the impulse response of the whole circuit of the 0 order hold. Okay. Now, we shall take up a little bit of simple mathematics that you all know how to represent the numbers in binary form by different convention. So, DSP algorithm will be used for special purpose DSP chips or the programs that will be quantizing the either the signal or the parameters. Now, there are three kinds of the three places where this quantization is coming. So, error will be generated at 3 points. One is input. Input, first of all, you have to scale it to that particular level, and then the input has to be quantized. So, the input error. Now, input is a signal which really does not alter the system property, all right. It will give you some output, say instead of 5.2, suppose you are giving an input 5. So, had everything else been ideal, then the output is just proportionately reduced, all right. So, input error is going to give you error in the output, but it is not going to affect the property of the system. Then, or the quality of the output. Then you have product, you are having multiplication inside, all right. So, you are having a finite bit length for the representation of any quantity, say 8 bit. So, an 8 bit number is multiplied by another 8 bit number, it may go to 16 bit, all right. Then you are truncating it. So, this is going to cause more of errors. Product of finite length quantities or variables, that is you can multiply by a multiplier or just two quantities, two variables may be multiplied, finite length quantities So, the product will have this gives a larger bit length. So, you have to truncate it. The third one, which is the most important one, is the parameter quantization. Parameter quantization, you can see if we change the parameter, the roots may change. Hz we say Bz by Az, we may write B0 plus B1 Z inverse and so on, 1 minus A1 Z inverse minus A2 Z to the power minus 2 and so on. Normally we put a negative sign because it is an these coefficients will come to this side, and if they are transferred you can write plus or minus, it really does not matter. Many books they follow this as a standard form. Anyway, these B0, B1, A1, A2 etc., these are the constants which if you quantize will be changing the distribution of roots. You must have studied in control systems root locus technique. So, there the last coefficient, the gain, if you keep on changing, the roots keep on changing. Now, here you are having multiple changes in all the coefficients. So, you can imagine all the roots will be changing in a very complex way, and sometimes they may go out of the unit circle. So, that may reduce the stability of the system. It is not only going to the unstable zone, even if they change their positions, the response is drastically affected. That we will see very soon. So, round of noise which may be positive or negative, they may cause a limit cycle oscillation. And noise, random noise. Now, representation of numbers, we may write a number in this form, where C is the coefficient associated with a particular radix R. Okay. So, in a decimal system we have R is equal to 10, in a binary system we have R is equal to 2. So, 25.564 we write as Ci 10 to the power I. So, that can be written as 2 into 10 to the power 1 plus 0 into 10 to the power 0 plus 5 into 10 to the power minus 1 plus 6 into 10 to the power minus 2 plus 4 into 10 to the power minus 3. If R is equal to 2, we write 110.010, that represents 1 into 2 to the power 2, okay, plus 1 into 2 to the power 1 plus 0 into 2 to the power 0 plus 0 into 2 to the power minus 1 plus 1 into 2 to the power minus 2 plus 0 into 2 to the power minus 3. So, if you work it, 2 to the 4 plus 2 6, 0, this is 1/4, 6.25.
In the last example that should be 5 into 10 to the
0, which one? 5 into 10 to the power minus 1,
the term previous to that.
0 into 5, sorry, not 20, 5 into 10 to the 0. Thank you. Thank you very much. Okay. I was writing something, I was having 20 in my mind. So, this is 6.25. So, for conversion from decimal to binary, we have say a floating point arrangement like this. Okay, 30.275. How much is it in the binary system? So, what we do, this part we divide by 2 and take the remainder 0, then that gives me 15 divided by 2, the remainder is 1, the quotient is 7, 7 divided by 2, the remainder is 1, then 3 divided by 2, remainder is 1, 1 divided by 2, okay, remainder is 0. So, we have 1, okay, and quotient is 0, all right. So, we take it from this way, it will be 1 1 1 1 0, okay, and the fractional part we keep on multiplying by 2 and start removing the integral part. So, 0.275 multiplied by 2 and we go downward is equal to 0.5. So, this is 0, 0.55, 0.55 multiplied by 2, so that is 1.10, so that is 1, 0.10 into 2, how much? 0.2, 0, 0.2 into 2, 0.4, that is 0, 0.4 into 2, 0.8 into 2 is 1.6, so 1, all right. Is this okay? And then 0.6 into 2 is 1.2 is 1, again 0.2. So, if it is 0.2, you are coming back to this same place. So, it will continue again 0 0 like that, 1 1 and so on. So, 30.275 will be 11110 point 0 1, go downward, 0 0 0 1 1 0 0 1 1 0 0. Will it be 2 zeros or 3 zeros? Check. 2 zeros, 1 1 0 0. So, it is like your recurring decimal, all right. So, it is not only in decimal system, also in binary system you can have a number which may not end, it may be endless, okay. Sorry. So, there are 3 types of representation in the binary system. One is sign magnitude, one is 1's complement, and the third one is 2's complement. Some of you have studied this in digital electronics. For the benefit of those who have not gone through this course, I will just briefly go through this. We will not go into the details of this representation. So, the negative number is always given by a 1 and a positive number by a 0 in the MSB, most significant bit. So, say minus 1.75 will be 11.110000. 1.75 is 0 1. So, this 1 is for the sign, the 0 is for positive sign, 0.110000. 0.75 is written like this. So, this is half to the power 1, half to the power 2 and so on. So, that gives me this. So, with B bits you have 2 to the power b minus 1 number of numbers can be represented. Okay. So, this is a very simple form. In one's complement form, for positive numbers it is same. For positive numbers it is same as the earlier one, that is sign magnitude form. For negative numbers, say 0.875, if you write it will be 0.1100111000 in the binary form. So, for minus 0.875 you just complement each bit. So, it will be 1.000111. Now, 0 can be represented in this ones complement form as 00.0000, say we have 6 bit. I can write also minus 0, that will be 11.1111. So, this and this both will be representing zeros in the ones complement form. In twos complement form, okay, let me write on this side. So, the same number 875 is positive number is once again same. So, minus 0.875 you just take the complement and then add 1 at the last bit. So, it was 1.000111, 1.000111. So, add 1. So, that gives me 0, 0, 1 plus 1, 0, 0, 0, then 1, 0, 0. So, it will be 1.001000. So, this will be the representation in the binary form for twos complement. This is as good as, this is same as subtracting 0.875 from 2. So, 2 means 10.0000 and 0.875 is 0.111000, okay, and you are subtracting this, okay, you are subtracting this. So, that will give you 1.00100. So, this is same as this. Addition of two fixed point numbers. If it is 0.5, which is 0.100 in the binary form, and 0.25, okay, 0.125, which is 0.001 in the binary form. If you add them together, if the total does not exceed 1, there is no problem. So, 0.625 is addition of 0.5 plus 0.125 in the decimal system, and it will be 0.100 plus 0.001. So, that gives me 0.101. The sign bit is not changing, okay. But if the sum exceeds, if the sum exceeds 1, that is rather exceeds the limit of 3 bits, we have a 3-bit representation. If it exceeds that, then we have problems. That carry will be causing overflow. So, 0.5 plus 0.625, if we add, this is 0.100 and 0.625 is 0.101, all right. If you add, this is 1, 0, 0 and 1, which is causing a negative sign basically. So, this will be causing an overflow, which is confused with the sign bit. So, actual sum is 1.125. So, 1.125 cannot be represented in a 3-bit system. The subtraction of two fixed points number this we can do by 2's complement. Say 0.5, we want to subtract 0.25 from here. So, that gives me 0.25, okay. So, 0.5 in 2's sorry, in 2's complement it is 0.100, okay, because it is a positive number, there is no problem. For a negative number 0.25 is how much, all right, and then complement it, it will be 1.101, okay. Is that all right? So, 1.101. Sorry, you have to add 1 for 2's complement. This is 1's complement, this is 2's complement, 1 1 1 Is it all right? 0, 1, sorry 1 and 1. So, 1.110, okay. Add them straight 0, 1, 0, 0, 1 and then neglect this, right. So, you drop this. So, 0.010, this is for 0.25. Is this all right? So, this carry is dropped. Otherwise 1.110, okay. Let us see 1.110, what will be 2's complement? Zero 0.010. You can do by a simple subtraction also. The 2's complement is simpler. You just take the negative quantity in 2's complement, positive quantity remains as it is. So, add them together, that gives you the result. Multiplication, this is somewhat involved. We see that suppose we have a 2-bit representation of two numbers, the product is a 4-bit number, all right. When you multiply specially, you get this problem. So, if you have 2-bit number for the integral part plus 2-bit number in the fraction part, then the product may give you 4-bit part in the integral part and 4-bit part in the fractional part. So, in a floating point representation, we write a number in this form where m is between half and 1, m is the mantissa. Okay. So, C is either positive or negative. For example, 4.5 we should write as 2 to the power how much? If I write 2 to the power 2, then I will get a quantity m which will be more than 1. So, it should be always next higher number which is some power of 2. Next higher number is 8. So, 8 into something, 8 into 4.5 by 8. All right. So, it is 2 to the power 3 multiplied by 0.5625. So, it will be 2 to the power, this 3 is 011 multiplied by 0.5625. If you write in a 4-bit representation, it will be like this, 0.5 plus 0.25 and so on. Is it all right? Similarly, 1.5 will be, next number is 2. So, 2 to the power 1 into 1.5 by 2. So, that is 2 to the power 1 into 0.75 and that is 2 to the power 1. So, it will be 001 into 0.75, 0.1100. Okay. 6.5 2 to the power 3 into 0.8125. So, that gives me 2 to the power 001 sorry 2 to the power 3011 into 0.1101, okay. 0.625 it will be 2 to the power 0 into 0.625, which will be 2 to the power 000 into 0.1010. So, like this any number you can express in terms of decimal binary forms. Let us now multiply 1.5 into 1.25. So, 1.5 is 2 to the power 1 into 0.75, that is 2 to the power 001 into 0.1100, okay. So, 2 to the power C1 into M1. 1.25 is 2 to the power 1 into 0.625, that is 2 to the power 001 into 0.1010, okay. So, that is 2 to the power C2 into M1, 2 to the power C1, C1 is equal to C2, okay, M2. So, addition will give me multiplication will give me 2 to the power C1, that is common, plus C2, okay, 2 to the power C1 plus 2 to the power C2, correct, into N2, okay. So, 2 to the power 010 into 0 point product of these two, so 0.1100, 0.1010, what is the product? 0000, 1100, then 0000, 1100, if I add 1 1 1, okay. Now 1 2 3 4 5 6 7 8, 1 2 3 4 6 7 8, so 1 0, so 0.0111 1 2 3 4, okay. If it is a 4-bit representation, then you have to truncate, all right. Now, if you have to add two floating point numbers for addition or subtraction, for that matter, for addition of two floating point numbers, see when you add 10 with 7, basically you put a 0 here. So, both of them are brought to the same level of representation, same number of digits, all right. So, you have to bring them to the same number of digits and then only you can add. So, 3.0 plus 0.125, what will be the addition of these two? So, 3.0 is 2 to the power 2 into 0.75, okay. So, 2 to the power 010 into 0.110000. 0.125 is 2 to the power 2, you have to bring the same index, okay, into 0.125 by 4, so 0.03125, which gives me 2 to the power 010 into 0.0000100, okay. So, if you add 3.0 plus 0.125, that gives me correct me if I am wrong, 0.125 by 4. So, that gives me this. So, this will be 2 to the power 010 into product of these two will become, sorry, this is sum. So, this will give me 0.1100 1100 100. Okay. So, we will take it up in further details later on if time permits, otherwise I leave it at this point. You can read it up from the books for further details of this. Now, quantization error, as we are discussing earlier. Sorry. In the direct form, the coefficients are appearing, the coefficients of the polynomials will be appearing in the structure as constants, as multiplier, is it not? In the other forms, that is, if you have cascaded form or parallel form, the constants of these are not going to affect all the roots, they are going to affect only that particular pair. For example, if I have say Az, okay, Bz by Az as product of some Bi okay, Bi0 plus Bi1 Z inverse plus Bi2 Z to the power minus 2 divided by 1 minus Ai1 Z inverse as Ai2 Z to the power minus 2, and I varying from say 1 to k. That means there are many biquads I have got in cascade. I could have also written this as some constant k1 by 1 minus Ai1 Z inverse minus Ai2 Z to the power minus 2 plus sorry A1 k2 minus A21 Z inverse minus A22 Z to the minus 2 and so on. I could have put in parallel forms, all right. So, here the two zeros and two poles only will be affected by quantization of these coefficients, whereas in the direct form all the coefficients, that is Bz by Az, and say B0 plus B1 Z inverse plus B2 Z to the minus 2 and so on. If you take the polynomial as it is and quantization of these will be affecting all the poles and zeros, all right. Here quantization of a coefficient, suppose forget about others, just one coefficient is changed, only this pole pair will be affected, others will not be affected. So, here we are restricting it within a certain group, restricting the sensitivity of a particular group of poles and zeros with the variation of these coefficients. So, this is much more robust. However, in this case the poles are restricted, zeros will be, zeros are not known, they are in a very complex mode, because if you add up k1 into a21, a22, k2 into a11, a12 and so on, all these terms will appear. So, here only the poles will be affected by the effect of variation of the poles these parameters will be restricted to poles, but these parameters will not be affecting the zeros independently. In normalized lattice, if you are having a smaller bit representation, then this is a very robust one, okay, very useful for smaller bit representation, but it needs lot of computation. Computation is more. In the other two cases, the number of elements required will be same as a direct form, a little bit of extra computation will be involved. So, these three representations, that is normalized lattice or cascade or parallel forms, they will be more robust compared to a direct form. Okay. Now, we will see the effect of quantization. Let us consider Hz as k varying from 1 to n, k varying from 0 to m. So, h hat z will be bk hat z to the power minus k bk hat is bk plus delta bk, the error due to quantization, actual value plus the error. Okay. Let us consider Az, okay, the poles. We can write this as 1 minus akz to the power minus k equal to 1 to n. This can be factorized, and I can write this as 1 minus z I z inverse I varying from, okay, I will write j equal to 1 to n, sorry, n, there it is an nth order polynomial having n roots. Okay. Now, let us see the sensitivity, let us see the change. Delta z I is sigma delta z I by delta a k into delta a k, that is shift in the sensitivity of the ith root with respect to any one constant multiplied by the change in that constant, that will be the small change due to a particular element, particular parameter. Similarly, if you sum up, then that will be the total change in the position of a particular root. Okay. Each root is dependent on all the parameters a1, a2, a3, a4. So, you make a small change in a1, a small change in a2 and so on. So, collect the total change. So, the total change in that ith root will be so much. Okay. Again k varying from 1 to n. Now, delta Az by delta Zi multiplied by delta Zi by delta Ak is equal to delta Az by delta Ak Z equal to Zi. So, change in this, the partial derivative of this with respect to any root Zi, okay, and if you compute that slope at Z is equal to Zi, that multiplied by the sensitivity of Zi with respect to Ak will be the sensitivity of this, the partial derivative of Az with respect to the coefficient Ak. So, from here delta Zi by delta Ak will be this divided by this. Okay. If you expand this delta Az by delta Ak, you can just see, take the derivative with respect to Ak. So, that will give me what? It is 1 minus A1 Z to the power minus 1, so A2 Z to the power minus 2 and so on. If I take Ak Z to the power minus k minus An Z to the power minus n, okay. If I take the derivative with respect to Ak, it will be Z to the power minus k with a negative sign. So, this will be Z to the power minus k. Similarly, if you do this, you will get Z to the power I and then pi Zi minus Zj. If we evaluate this, j equal to 1 to n, j not equal to I, all right, and there will be a negative sign here. So, that will make it positive. Okay. Now, you see this term, what does it mean? Suppose the poles, we are now considering only the denominator factor poles. If the poles are very tightly clustered, okay, there will be complex conjugates, no? They will be always appearing in the form of complex conjugate. Now, these are the vectors Zi minus Zj. Say, suppose this is the ith one. So, these are the Zi minus Zj quantities, Zi minus Zj. Okay. Now, if you take the products, if this Zi shifts a little, it is quite a big change, all right. It is something like 0.01 to 0.02. The difference is, say if it is at a distance of 5.1, if it shifts to 5.2, there is not much of a change, 5.1 to 5.2, but the distance between the two poles, if they are all in close cluster, it may be from 0.01 to 0.02, it is doubled. Do you get my point? So, the denominator which is the product of such vectors, all right, finally will give you a big change, all right. So, they are very, very sensitive, especially when they are in close cluster. Same is the case with the zeros, all right. This is a narrow band pass filter basically. If you are having a close cluster here, that will correspond to a low pass filter, narrow band low pass filter. Okay. Low pass filter roots are somewhere close to the real axis, and band pass filters here away from the real axis. Now, let us see what will be the effect on this. sorry. We have, say, for a quadratic representation, we may have something like this. We can write a quadratic form in this fashion also, that is 1 by 1 minus 2r cos theta z inverse minus z to the power minus 2 or plus r square z to the power minus 2. Okay. Suppose we have the biquad representation like this, 1 minus 2r cos theta z to the power minus 1 plus r square z to the power minus 2. It is in a quadratic form. If the roots are complex, if the roots are simple on the real axis, then there is no problem, the roots are here. Okay. If they are complex, then we can represent by this form. So, the roots are at r e to the power j theta and r e to the power minus j theta. Suppose we quantize these two quantities, then what are the possible values? So, we will take it up in the next class. The time is just over. What will be the effect on quantization of these quantities? Okay. Thank you very much. I will take it up on